Today I'll be speaking on the so-called conformal blocks and their dual realization. Basically, I'll be discussing conformal blocks living on a torus, and this is the subject of these two papers, but also I will give you a short review of what happens in the sphere case, and this is why I slightly changed the original title. So let me make a preliminary comment that the main idea behind this activity is that conformal blocks living on a conformal boundary are exactly the length of particular geodesic networks stretching the bulk with endpoints attached to the conformal boundary. And our main formula here is that classical blocks are equal to geodesic.
I think it must have been just a loose connection. I just pressed it in.
Yeah, but it's not.
Try to switch it.
Yeah, it works. Okay, once again. So our main formula here is that classical blocks are equal to geodesic length, and we call this block length correspondence, which is just a semi-classical version of the standard ADS3C52 duality. So here is the plan that I hope to realize today, and I will start from a short review, as I promised you, of the this block length correspondence in the sphere case. Then I will switch to the torus, and we'll discuss various semi-classical conformal blocks and how they're related to each other. The point is that they're not quite independent and related to each other by a chain of connections. And then I will switch, I will use the symmetry argument, and will explain that the existence of these different semi-classical blocks is not occasional, because they can be traced back to the existence of the truncated, not truncated, contracted Virasoro algebras, because conformal block is quite model independent. It's completely fixed by using symmetry algebra, and this is why various derived objects of conformal blocks, like semi-classical blocks, can be understood in terms of operations done with the symmetry algebra. Then I will consider the so-called classical block, which is just particular semi-classical block, and will give its holographic interpretation in terms of geodesic networks stretched on the thermal IDS in the case of one-point correlation function. Okay, and then traditionally I will summarize the results obtained and discuss future perspectives. So let's start. We are on a sphere, and suppose we have endpoint correlation function composed of and primary operators with conformal dimensions delta. They are inserted on a plane, so we identify plane and sphere. So they inserted on a plane in different points labeled by z and z bars. Those z bars are I decided just to write down the holomorphic part of correlation function, and I will explain it some later. And we know that correlation function can be decomposed into conformal blocks by using particular OPE channel, and the expansion coefficient are identified with the structure functions, which are given here by C, and also we use a particular range of summation given by conformal dimensions. So dividing the correlation function into holomorphic and anti-holomorphic parts, we observe that the model independent part of correlation function is given by the so-called conformal block, which depend on the coordinates of operator insertions, on external dimensions delta, and on conformal dimensions of the exchange channels, which are denoted by deltas tilde. Okay, and also the conformal block depends on the central chart. And we know that in a given OPE channel, the conformal block is conveniently depicted by, say, the fishbone diagram, where straight lines correspond to external legs, while wavy lines are just exchange channels. And three of these coordinates, which parameterize the external legs, can be fixed by using global conformal symmetry to prescribed values of coordinates on the plane, namely to 0, 1, and infinity, say. Okay, in what follows, we will be distinguishing between different semi-classical limits of conformal blocks, and these limits depend on particular behavior of conformal dimensions. So there are two types of conformal dimensions, which we call heavy and light. And heavy operators, or heavy dimensions, means that conformal dimension grow linearly with central charge, while in the case of light operator, conformal dimension remains fixed independently of a particular value of the central charge. So having this in mind, we distinguish between three types of conformal blocks. And the first type is just what people call global conformal block. This is the case when all operators are light. Another type of conformal block is, in some sense, opposite to global conformal block, is the so-called classical conformal block. In this case, operators are heavy, and there is also a bulk of heavy light blocks which interpolate between these two extreme regimes. So now we switch to classical conformal block, and there is a lot of evidence in literature that in the semi-classical regime, when the central charge tends to infinity, the conformal block exponentiates as follows. It means precisely that the original quantum block is given by exponential with the exponential factor called classical conformal block, while these epsilon and epsilon tilde are called classical dimensions. They are given by ratios of original conformal dimensions and the central charge. So classical conformal blocks could be quite complicated functions with many interesting properties. For example, in the 4-point case on a sphere, classical conformal block can be shown to satisfy the so-called Penn-Levesque equation. But for our purposes, we can use this so-called heavy light perturbation expansion. Drastically simplifies the analysis of classical conformal block. It was originally introduced by Fitzpatrick, Kaplan, and Walters. Unfortunately, this name is somewhat misleading, because by the heavy light perturbation expansion, I mean that a part of heavy fields, let me remind you that all fields in the classical conformal block are heavy. So a part of heavy fields are heavier than other heavy fields. So there are no place for light fields. Okay, and in the case we'll consider below, we take two operators to be background heavy operators, and in that sense they form background for other heavy operators. So we can introduce background and perturbative operators, and this choice greatly simplifies the whole analysis. So okay, as the background heavy operators, we choose the last two operators with equal dimensions and denote their respective classical dimension as epsilon h. So in order to develop this perturbation theory, we introduce small parameters given by these ratios, and then the classical conformal block is expanded as follows. And we know that the zero of approximation here corresponds to the classical conformal block of 2-point correlation function, and these 2-point correlation function correspond to taking two background operators. And in particular, this explains why we took these dimensions equal to each other, because two-point correlation function should be not vanishing. Okay, so the corresponding classical block is 0, and the first non-trivial correction is given by this term, which is called linearized classical block. Now, the two background operators create non-trivial geometry in the bulk, and it's shown that this is an asymptotically ADS-free geometry, which is either conical singularity or BTZ black hole, depending on this parameter alpha, which is expressed in terms of heavy dimensions. And for the conical singularity, this alpha parameterizes the angle deficit. In this case, alpha squared is positive. And we see if we add more mass in our space, this alpha goes to be imaginary, pure imaginary, and then this next singularity of conical singularity evolves to the BTZ black hole, and the singularity is now covered by horizon. In the case of the conical singularity, the corresponding metric in the bulk is given by this expression, and we see that the metric coefficients depend only on the radius, and it means precisely that we can do a partial Hamiltonian reduction and restrict the dynamics to the two-dimensional slice of three-dimensional geometry, and this two-dimensional slice has negative curvature, and in fact this is just a Poincare disk. So in this picture we see that two background heavy operators create background bulk geometry, while perturbative heavy operators correspond to test particles propagating in this geometry, so that the word lines form a particular network of geodesic segments. And on this picture, this network is depicted here on this two-dimensional Poincare disk. And points WI correspond to boundary attachment of the external legs of the original conformal block. So we claim that the linearized conformal block up to global conformal transformation is equivalent to the length of this geodesic graph, where the length is composed of lengths of different segments here, so that this sum is minimal. This is why we call this network geodesic. And these two functions, modular conformal transformation, coincide. There is a simple mnemonic rule which helps us to build this geodesic network for a given conformal block diagram. And to this end, we draw in black these two rightmost operators. So they're heavy background operators, while other lines correspond to heavy perturbative operators, including exchange channels. And then we just erase these two rightmost operators, and the remaining diagram should be inserted into the two-dimensional disk, so that this endpoint goes to the center of the disk, while endpoints of the external legs are attached to this boundary circle, which is the conformal boundary. Now we claim that modular conformal transformations, these two functions, linearized block and the length, are equal to each other. I should say that in the endpoint case, these functions are not explicitly known, because finding them is a very complicated problem related to solving a system of algebraic equations. But there is the existing theorem claiming that under appropriate conditions, and we don't know how to find these functions explicitly, these left-hand side and right-hand side should coincide. So this relation provides the semi-classical ADS-CFT correspondence in this case. Okay, now we turn to the Torus case, and of course our primary goal is to extend this block length correspondence from the sphere to arbitrary Riemannian surfaces. And the torus case here is the first non-trivial case. It corresponds to the Riemannian surface of genus 1. And I should say that contrary to the sphere case, 0-point function and 1-point function are quite non-trivial function on a torus. For example, 0-point function is just a Virasoro character, while 1-point function is as much complicated as 4-point function on a sphere. Moreover, these authors claim that there is a map between 1-point torus function and 4-point sphere function. So, I mean that 1-point torus blocks are quite non-trivial functions to study. And in general, I would like to say that classical conformal blocks are very poorly understood, except for sphere case maybe. And in this respect, I would like, poor understood for arbitrary genus G, arbitrary Riemannian surface, and arbitrary number of operator insertions, that is in the endpoint case. And in this respect, I would like to note a recent interesting paper by these authors who claim that they have a general calculation scheme to find Virasoro quantum blocks, and possibly that will help us to find the corresponding classical conformal blocks. So we see that classical conformal blocks is just a kind of terra incognita for two-dimensional conformal field theory. Okay, and let's now consider 1-point torus block. And by analogy with the sphere case, it's defined as a holomorphic part of 1-point correlation functions living on a torus for some primary operator with conformal dimension delta. Here C is just a structure constant. It is model dependent, and conformal block is model independent. It's completely fixed by Virasoro symmetry. And conformal block on the torus is given by this power series in the modular parameter Q, which is related to the modulus of the torus tau. And the expansion coefficients here are given by these matrix elements of the primary operator, where Bryant-Cat vectors are given in a standard way by acting with Virasoro generators on a primary vector. And matrix B with upper indices is just the inverse of the Gram matrix, which define inner products of vectors and the corresponding Fermat module. Yep. Maybe you are right. Sorry. Yeah, that's right. And I'd like to explain this by considering this trivalent vertex. So it's just one structure constant. Thanks. Okay, and graphically, the 1-point conformal block on the torus can be given by this tadpole diagram, which can be understood as follows. This is quite similar to the way we consider 1-point torus functions. Indeed, it can be built starting from a CFT on a plane, then we conformally map plane to a cylinder, and then identify edges of the cylinder to obtain a torus. And to find this tadpole diagram, we also consider trivalent vertex on a plane, and then identify edge states of two external legs to produce this loop. So the loop is for exchange channel, and this external leg corresponds to the primary operator. Now we see that the function of torus block depends on three parameters, including external conformal dimension, exchange conformal dimension, and the central charge. So we consider various regimes of how conformal dimensions behave themselves with respect to the central charge. And we distinguish between four types of blocks. The first block, first two blocks actually, are related to the case when we choose two conformal dimensions to be light. It means that they are not related to the central charge, and when the central charge tends to infinity, they remain fixed. So there are global and light blocks, and the global block is related to SL2 subalgebra of Virasoro algebra, while light block is related to the leading asymptotic in the so-called C-recursive representation of torus block. Another option is the heavy light block, when one of operators is heavy and the other one is light. And in fact, it can be shown that there is just one heavy light block, because related to the following choice, the external leg is light and the internal loop is heavy. The opposite option does not exist, just because the expansion coefficient of the torus blocks already first coefficient has a pole in the exchange dimension. Okay, and in particular, it means that there is now this so-called vacuum approximation, which was instrumental in calculating the entanglement entropy on a sphere, because we cannot set this loop to zero, contrary to vacuum blocks on a sphere. Another semi-classical block is the classical conformal block itself, and this is the case when two operators are heavy. So the respective conformal dimensions grow linearly with the central charge. And in particular, it's interesting to consider the case when the loop or the third pole diagram is much more heavier than the external leg. In this way, we obtain the linearized classical conformal block, and some later will show that it's this linearized classical conformal block which can be realized holographically in the formal ideas. So our point here is that all these four types of semi-classical torus blocks are not quite independent, and instead they are linked to each other by a chain of connections. So now let us start from considering global torus block, and we know that Virasoro algebra of a CFT living on arbitrary Riemannian surface has a finite dimensional subalgebra SL2. So the global block by definition is just the block associated to this SL2. Okay, we see that it does not depend on the central charge, and in fact the global block is just a d-dimensional conformal block restricted to 2 dimensions. Okay, in this case, the general expression for the quantum block drastically simplifies, and the corresponding expansion coefficient are given by these matrix elements, where instead of all Virasoro generators, we have only L-1, L+1, and L0, which just the commutator of this L+-1. So these three generators form SL2 subalgebra, and the expansion coefficient can be explicitly calculated and shown that they can be packed into the hypergeometric function of this form multiplied by this power law prefactor. And as a consistency check, we can consider the limiting case when the dimension of the external leg tends to 0. And in this case, this global block is just given by this expression, and we see that this is the character of SL2 algebra, and the form of this function indicates that there is just one state on each level of the corresponding SL2 module. Now, the most important thing about global block is that it satisfies the second order differential equation given here, and we would like to consider the regime where conformal dimensions tend to infinity in a coherent manner, meaning that we introduce some large parameter kappa, and the sigma and sigma tilde are just rescaled conformal dimensions. So from the general theory of differential equations, we know that in this case the solution exponentiates like this where function g is given formally by this integral. And actually, this is very important result for us, because some later we will show that this exponentiated global block is directly related to the linearized classical block. Okay, another comment is that on the sphere, we already met this kind of second-order differential equations, which are just the so-called Casimir channel equations, and actually the appearance of this second-order equation is not occasional. Okay, now we consider another semi-classical block with light operators, and this is the light torus block, and in general and can be defined as a leading asymptotic or the quantum Virasoro block when the central charge tends to infinity. And in this regime, by the way, we just had this power law prefactor, and since it diverges in this limit, we just moved it on the left-hand side to single out the finite part of the conformal block. So this leading asymptotic is the light block, and the most important thing about light block and global block is that they are related to each other by the relation of this kind, where function phi is the standard Euler function, which defines in particular Virasoro character. And having this prefactor 1 minus q says that global and light block are different by this prefactor, which is truncated Virasoro character. Okay, a few comments are in order. So first of all, this light block in one point case is the leading asymptotic for the so-called C-recursive relations which define one-point quantum torus blocks. And another important observation that this factorization property actually is general for any Riemannian surfaces and for blocks with arbitrary number of operator insertions. So in the sphere case, global block and light block are equivalent, they are equal to each other, and following results of these offers, we now know that the sphere case is an exception, but in general, a light block and global block are related by this relation. Okay, now we would like to use the symmetry argument and show that all the semi-classical blocks are related to particular contractions of the Virasoro algebra. And as I have already noted, the conformal blocks are model independent, they are completely fixed by symmetry algebra, and it means precisely that any semi-classical blocks that follow from original quantum block should be somehow related to operations done with the symmetry algebra. And indeed, this is the case, and to this end we consider, first of all, Virasoro algebra, which is given by these standard commutation relations. And as we consider also primary operators, here we give how the primary operators transform under Virasoro transformations. So now let me remind you what the Inonu-Wigner contraction is. So this a kind of limiting operation if you have an algebra, and this algebra is parameterized by some small parameter, then you can send this parameter to 0 to obtain another algebra. And a canonical example here is how Poincare algebra is related to ADS algebra, or Galilean algebra is related to Poincare algebra. So in the first case, we have cosmological constants, so we can rescale generators of ADS algebra with Halt's cosmological constant and then send it to 0 to obtain Poincare algebra. In the case of Galilean algebra, this is just the speed of light, and send in the inverse speed of light to 0. We obtain Galilean algebra from Poincare algebra. So in our case, Virasoro algebra is parameterized by the central charge. So sending to zero the inverse central charge, we can study various contractions. Okay, consider now general rescaled Virasoro generators, which are given by this expression where gamma is some function of integer parameter m. Then we distinguish between two main choices when the Virasoro generators are rescaled in this way. It means precisely that the finite dimensional part of Virasoro generators remain intact, while other operators, other Virasoro operators are rescaled into different ways. So since we also consider primary operators, we can show that this transformation law reduces to this general relation saying that the primary field is still SL2 primary field, but with respect to these higher order Virasoro generators, it's just a singlet. Okay, and doing these contractions, we observe that in the first case, the Virasoro algebra decomposes in two parts. The first part is SL2 subalgebra, and the other part is infinite dimensional abelian factor, and this is expressed by these two lines. And we see that the whole contracted Virasoro algebra is just a semi-direct sum of SL2 and this infinite dimensional abelian factor. In the second case, this contracted algebra now contains, instead of abelian factor, the Heisenberg algebra, which is given by these H with the respective commutation relations. So for these two contractions, we have two contracted algebras, which are both semi-direct products of finite dimensional SL2 and infinite dimensional factor, which is either abelian algebra or Heisenberg algebra. So our main proposition is that light and global blocks are just associated blocks which can be calculated using these two contracted algebra. In the first case, we obtain a global torus block, and in the second case, we find the light torus block. In particular, it's clear why global block is related to singling out SL2 subalgebra. This is because we consider irreducible representations, and it means precisely that this infinite dimensional abelian factor is trivially realized. It's not the case for the Heisenberg algebra, and calculating the associated block gives rise to that prefactor related to Euler function. Now we consider one more semi-classical block, which is the heavy light torus block. And as I explained earlier, one of dimensions, external dimension, is light, while the loop is heavy. So the corresponding heavy light torus block can be explicitly calculated up to high enough order in the modular parameter, and it's given by this inverse Euler function. So it's also, thank you very much, it's also not independent, and we can show that the heavy light block is just a limiting case of the light block. So considering the light block and sending the internal dimension to infinity, we reproduce this heavy light block. So also we observe that since the heavy light block does not depend on conformal dimensions at all, it's just the 0-point block or Virasoro character. And this situation is quite similar to what happens on a sphere, where these relations were observed for 4-point blocks and 5-point blocks. Okay, the heavy light block also admits this Virasoro contracted algebra interpretation. In this case, we rescale all Virasoro generators, including the SL2 part. and show that the contracted Virasoro algebra commutation relations in this case take this form, which up to linear transformation, I mean changing the basis, we can cast this commutation relation into the standard Heisenberg algebra commutation relation form. So calculating associated conformal block, we arrive exactly at this expression. So up to now we consider it 3 different semi-classical blocks, and they are all related to particular Virasoro algebra contractions. Finally, we consider the so-called Torus conformal block, classical Torus conformal block, and in this case all operators are heavy. So the respective dimensions grow linearly with the central charge, and we can substitute these dimensions into the conformal block and expand the resulting function around the infinite value of the central charge. So in this way we obtain some Lorentz series, which has a principal part, which has a regular part, and the respective coefficients are just some formal power series in the modular parameter, with next level expansion coefficient being some rational functions of classical conformal dimensions. And the most important thing about the classical block is that at large C, the principal part of this expansion goes to 0. Less obvious is that the regular part exponentiates. And it follows that the one-point torus block is asymptotically equivalent to this expression at large C. And this function, which is called classical conformal block, can be explicitly calculated up to high enough order. So the first coefficient is given here. In particular, we see that it has a pole with respect to exchange dimension. Okay, so we see that we have 4 types of semi-classical conformal blocks, and 3 first blocks, which are global light and heavy light blocks, are just limiting cases when we send the central charge to infinity, while the classical block is the large C asymptotical, the original quantum block. Unfortunately, there is no any interpretation in terms of contracted Virasoro algebra, but I believe that there should be kind of deformation theory with respect to small inverse charge, starting from some contracted Virasoro algebra, which takes account of all these corrections in the central charge. So this is not done yet, and actually I believe that up to now we consider classical blocks as a kind of asymptotic expansion around infinite central charge, but there should be some symmetry algebra, Virasoro algebra formulation in the spirit of these contracted Virasoro algebras. Now we consider the linearized conformal block, and to this end we introduce this called lightness parameter, which is just the ratio of 2 conformal dimensions, and then changing from the original classical conformal dimensions to delta, the lightness parameter, and the external conformal dimension, we can reorganize the whole conformal block function in terms of the double series expansion in delta and epsilon tilde, and find this expression which says that we keep terms at most linear in the external conformal dimension. So instead of the power series in the modular parameter, for the linearized conformal block we have these 2 terms, where the second term is given by power series in the lightness parameter, while the expansion coefficient are just some rational function of the modular parameter. So this is the point where we should recall about the global block, and we conjecture that exponentiated global block is equal to the exponentiated quantum block, that is, it is equal to the linearized classical block. So recalling that function which appeared for the global block, we see that modular this logarithmic contribution, these two functions just coincide. And the most important thing about this conjecture is that for the global block we know some formal integral representation which is given here. So we conjecture that the linearized conformal block on a torus in the one-point case is given by this integral. And finally, let me comment that this relation is analogous to what happens on the sphere case and for 4-point blocks and 5-point blocks. Now we realized these linearized conformal blocks in terms of particular geodesic networks stretched in the three-dimensional bulk, and we see that we can show this explicitly, that taking this tedpole diagram of one-point conformal block on a torus, we arrive at particular tedpole geodesic diagram embedded into the thermal ADS space, where thermal ADS is just the usual ADS space with periodic time. And the block length correspondence in this case claims that a linearized conformal block is equal to this sum of three terms, where last two terms are just lengths of this external leg and a loop, and the first term is just a gravitational action evaluated on the formal ADS background. Okay, so just to remind you what the formal ADS is, it's given by this metric where tau is the modulus and coordinates, time coordinate is periodic with this 2 pi period, and the radial coordinate runs from 0 to infinity, and at infinite radial distance we find a conformal boundary. And this boundary has a topology of a torus, so the formal ADS is just a solid torus characterized by this modulus. And this torus is not general because the modulus is pure imaginary. It means precisely that if we realize the space, I mean, if we realize torus as a rectangle on a two-plane with identified edges, so in this case we have very particular rectangle without twists. Now this is my final slide, and first of all consider the case of 0-point conformal block, that is, we just switch off the external leg, and in this case the corresponding graph is given by a circle running around this dashed line which correspond to 0 radius. And the total action is, in this case, is given by two terms. The first term is the gravitational action evaluated on thermal ADS, and the second term is the circumference of the loop, which can be easily computed from that metric on the previous slide. So in this 0-point case, we find this expression in terms of tau, and coming back to modular parameter, which is related with tau by this formula. Tau is just proportional to logarithm of q. So we see that this is the logarithmic contribution seen on the previous slides. And if we switch on the external leg, we also can show that more general duality holds. And in this case, this arm has three terms, including the length of the leg, and the correspondence, what is more important, holds in the so-called low temperature approximation. This is because we know that on the gravity side there are a lot of saddle points parameterized by different values of a modular parameter, and the formal ADS corresponds to infinite modular parameter, contrary, say, to BTZ black hole, which correspond to zero modular parameter, and they are related by modular transformation. Okay, so our claim is that the block length correspondence in this case is valid in the low temperature approximation, where the temperature is just the inverse modular parameter. So now let me summarize, and we consider it Torus conformal blocks, and observed that there are 4 different types of semi-classical blocks, and we established a chain of connections between these different semi-classical blocks and explained the appearance, the appearance of semi-classical blocks from the Virasoro algebra perspective. Also, we holographically realized the one-point torus blocks and the corresponding geometry in the bulk is just the formal IDS, and the correspondence holds, as I said before, in the low temperature regime. So there are also some open questions, and unfortunately I have no time to list them. Thank you very much. Mm-hmm.
I was wondering about the possible connection with n=2 theories. For instance, for the torus, with one insertion, you have n=2 with the matter in the adjoint. This is the simplest example I can think of.
It's not n=2.
So Nekrasov partition functions, if there is any via some AGT conjecture, I don't know.
No. The claim was that one-point torus blocks are related to 4-point sphere blocks. So there is a complicated map which relates these two functions, and in particular it would be interesting to understand how
I was referring to the fact that the conformal blocks or the correlation functions are related via some AGT conjecture, you may think, to the Nekrasov partition functions. So it's Cyber-Witten theory, partition, but with the supergravity backgrounds.
You mean AGT duality?
Yes, AGT.
For us, it's just a calculational tool, actually. We suppose that we have some expression for conformal block, and this expression can be obtained in various ways. It can be done using Zamolodchikov recursive procedure. It can be obtained by using AGT combinatorial representation or monodromy method, but for us, it really doesn't matter which way we used. We need a final expression for this function.
One question is, how do you see modular bootstrap on the torus?
We have not seen it yet because we know that correlation function is modularly invariant, but conformal blocks are not. So it would be interesting to check how these modular transformations of conformal blocks are reflected in the bulk. So how going between different saddle points of gravitational actions using this modular transformation is reflected with modular properties of conformal blocks. It's open question, actually.
If we don't have any other question, let's
thank you very much.
Speaker again. Next will be